So the next thing we want to look at now is IV characteristics. Characteristics of one, a conductor. 2, a filament lamp. Then 3, a semiconductor diode. So we want to look at the IV characteristics of this particular component. The first one is a conductor. The next one is a filament lamp. And the other one is a semiconductor diode. Those are the IV characteristics we want to look at. I there represent current, V represents the potential difference. So basically, what we are looking at is the graph of current against potential difference, which shows how the current changes with potential difference for a conductor, a filament lamp, and a semiconductor diode. So we start with the very first one, which is for a conductor. Now, remember that Ohm's law explains that the current flowing through a conductor, or the current flowing through a uniform conductor, is directly proportional to its potential difference, provided temperature is kept constant. The current flowing through a metallic conductor is directly proportional to its potential difference, provided temperature is kept constant. So conductors, invariably, most of them are classified as ohmic conductors, which basically means that they obey Ohm's law. So if I plot the graph of current against potential difference for a conductor, it's going to be a linear relationship. Linear relationship there means a straight line relationship, because the current flowing through a conductor is directly proportional to its potential difference. So the IV characteristic of a conductor is like this. Graph of current against potential difference for a conductor is going to be a straight line relationship, because the current flowing through a conductor is directly proportional to its potential difference, provided temperature is kept constant. So if the potential difference is applied in the forward bias, the current flowing in the conductor increases directly proportionally to the potential difference. If the potential difference is reversed, the current will then flow in opposite direction. In the same way, the current is still directly proportional to the potential difference. So we can say that in a conductor, the current changes linearly with potential difference in the forward direction as well as in the reverse or backward direction. So we can say in a conductor, the current changes linearly with potential difference. In the forward bias as well as the reversed or backward bias. What do I mean by forward bias and reverse or backward bias? So let us say you have a conductor here that is connected to a voltage source. This is the forward bias. So we expect that the current flows from positive to negative. So this end is positive and this end is negative. So current flows in this direction. If we reverse the polarity of the terminals of the conductor, let us say we then connected it like this, negative, positive. So this end is negative, this end is positive. The current still flows from positive to negative. That means that the current is now flowing in the reverse bias. So a conductor allows current to flow in the forward bias as well as the reverse bias. And the conductor allows current to flow in the forward bias as well as the what? The reverse bias. However, the current flowing is directly proportional to the potential difference in both directions. Alright. Then number 2, a filament lamp. Number 2 is a filament lamp. Filament lamp. The symbol for a filament lamp is like this. That is the symbol for a filament lamp. Now, in a filament lamp, the changes in temperature is considerable. The change in temperature is considerable, which simply means that when a filament lamp is conducting, the increase in temperature will be significant. Therefore, a filament lamp will not obey Ohm's law. Because in order for Ohm's law to be applicable, the temperature should be kept constant. That is why Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference, provided the temperature is kept constant. So most metals, the change in temperature in most metals is not considerable. That's why we can say that metals are ohmic conductors. Most metals are ohmic what? Conductors. But a filament lamp is not an ohmic conductor. The reason for that is that the change in temperature for a filament lamp is considerable. So as the current flowing through a filament lamp increases based on the change in the potential difference, as the potential difference applied to the filament lamp increases, the current flowing through the filament lamp also what? Increases. Then heating effect occurs in the filament lamp, which causes the temperature to increase. And because the filament lamp is a conductor but it's not a ohmic conductor, as the temperature increases, then resistance of the filament lamp is no longer constant. And according to what we have explained before, when the temperature of a conductor changes significantly, you expect that the resistance should increase. So in a filament lamp, as the PD applied to the filament lamp increases, the current increases. Therefore, the heating effect in the filament lamp increases, which causes the temperature to do what? To increase. Therefore, resistance in the filament lamp increases. So if I sketch the graph of current against potential difference in the filament lamp, as the PD increases, the current increases, and temperature increases, which causes the resistance to increase. Now, on this graph, the resistance represents the inverse of the gradient. Why? Because resistance is the ratio of the PD to what? To current. So if I plot the graph of current, so if I have I becomes 1 over R dot what? V. So if I plot the graph of I against V, the gradient of the graph is the inverse of resistance, which is referred to as conductance. The inverse of resistance is what is referred to as what? Conductance. So if you plot the graph of I against V, the gradient of the graph is the inverse of resistance, which is known as what? Conductance. And according to what we are saying there, when the temperature, when the PD applied to a filament lamp increases, the current increases. Hence, heating effect in the filament lamp increases, which causes the resistance to increase. As the resistance increases, 1 over resistance, which is the gradient of this graph, reduces. So, how do I illustrate that? Graph of current against potential what? Difference. As the potential difference applied to the filament lamp increases, the current increases. Therefore, heating effect in the filament lamp does what? Increases. And resistance will increase. But the gradient of the graph is not resistance. It's the inverse of what? Resistance. Therefore, the gradient of the graph reduces. Like this. Is that okay? This showing reduction in what? In gradient. The graph becomes less steep. But it does not reduce to 0. The gradient of the graph does not reduce to 0. The reason for that is that the conductance, which is the gradient of the graph, will not go to 0. Which means that the resistance will not go to infinity. So when you are sketching this graph, you should just sketch it for reduction in gradient. The graph should not become completely flat like this. This happens in the forward direction as well as the reverse direction. It happens in the forward direction as well as the what? The reverse direction. So in a filament lamp, you can write as the PD increases, current increases, heating effect increases, heating effect increases, hence temperature increases and resistance increases. This causes the gradient of the graph in bracket inverse of resistance to reduce, but it does not reduce to zero, but it does not reduce, it does not reduce to zero. This is applicable in the forward and reverse directions. Alright. So that basically explains how changes in temperature affect the graph of current against potential difference in a semiconductor diode.